Okay, so good. So where were we last time? So we proved this lemma as well, right? So this the lemma that we proved last was this R skip lemma, which said that if like the left hand side is related to the skip rule, then it must be the case that you can take a number of silent steps from VC1 all the way to some skip, right? So we proved that as well. And what we're going to do now is we are going to use all of these separate lemmas that we had, this match with lemma and then this R skip lemma and so on, in order to prove the backward simulation. I mean, really, that is where we are getting to, right? We want to prove that trace inclusion for backward simulation. So here is the actual lemma. This is the same lemma as what we had for um, the simulation where the steps match one to one, right? So the so if VC2 can generate NS and the state VC1 is related to VC2, except that you have an N here, then VC1 also generates the same trace NS, right? And just like before, we are going to prove this by induction on the definition of traces for VC2. So let's do that, right? Some cases VC1 first. So this is this auto makes the truncation go through. We now have to handle the case where this is actually a skip, right? So VC2 is actually a skip, and we have to say something about VC1. And here, unlike earlier, where we used this idea of totality to directly jump, we have to use something more. It's not just you can take a single step. You can actually take multiple steps to multiple silent steps. This is the addition that we have, right? You can take multiple silent steps, and each of those can match the skip rule. And I mean, so we've sort of used the totality in our lemmas, but we are going to use our lemma directly, right? So let's do cases VC1 to just destruct it. And the thing that we are going to do is first apply skip, R skip. And what does R skip tell us? R skips tells me that if I have the left hand side related to skip on the right hand side, then it must be the case that I can take several silent steps in order to also get VC1 to skip. Right? This is what we just proved in the previous lemma. So we are going to use it here, right? And then do first order. So what it does, so where we are applying this is we are applying this on H, right? Apply R skip on H and do first order. So this is going to be converted to this silent C step, multiple silent C steps to skip, right? Let's keep that on the side. And what we also know is this other lemma, which we proved, step to termination, right? Which is going to say, right? So if you have VC and then it takes multiple silent steps to termination, then we know that by the constructor, we know this particular state generates this trace. Thanks to step to termination, we also know that VC also generates the same trace, right? So this is also something that we proved earlier. We are going to apply that to transform this goal into something that exactly matches the hypothesis that we have. So this matches the hypothesis. We don't actually care about what the state there is. So we do E assumption to pattern match it that unifies, and we are done with the termination case, right? We still have two other cases. The first one is the silent step where both sides take a step, right? And then we have the noisy step, the output step, where both sides also take a step. So let's do the similar thing that we had done for the previous proof. So we are going to draw a figure of what we have currently. So we have a relationship between VC1 and VC, VC1, VC related by Rn, right? And we have C step VC none to VC prime because we are doing induction on the right. We have that step, right? We also have the induction hypothesis. Let's come back to that. So because this is the silent step, we have none label here. It goes to VC prime. And what are we asked to prove? We are asked to prove that VC1 generates ns. So this VC1 generated ns. And what do we know? We know that VC prime generates ns. So if you look at 80, right, 80 here, we know that VC prime generates ns. So we have to show that if this generates some trace ns, then this also generates the trace ns, right? And here, what we are going to do is we are going to apply our match step lemma. So we are taking a step here, but what match step tells us is that this could involve a number of silent, 0 or more silent steps, and then one actual step where the labels match. Right? That's what match step is going to tell us, and let's apply that. Right? Let's apply that in H1. What is H1? H1 is this relationship, right? This relationship here. So we will get the match step. Let's do first order to break it apart. We are no longer going to use one step and agree on termination because match step has already did that for us. So let's clear that out. So clear is this tactic which just removes hypotheses. All right, so let's clear it out so that this becomes manageable. So if you again draw what we have, so match step has actually told us that there are a number of silent steps and then one step that matches the label, right? So that is what we have. And what are we asked to show? We need to show that VC1 generates NS. VC1 generates NS. And what we have that VC prime generates NS. So that is here, 80, VC prime generates NS. So I have to show here, if you sort of stare at it, right? Oh, I know that this is all generating silent labels. So I should be able to, if I need to show this generates NS trace, I can show that X also generates NS trace, and similarly X0 also generates NS trace, right? Stepping through each one. We've done all of the hard work. We've actually proved this using helper lemmas. One thing that we proved is silent generate backward, right? What does that say? If there is a number of silent steps and you know that VC prime, right, generates NS, then VC also generates NS, right? So this is what we had proved earlier. So let's actually use that now, right? So we are going to use that on here, right? So that our proof sort of becomes gets closer, right? We need to show this one. It gets a little bit closer. So when I apply this, right, I need to show that there are a number of silent steps, and that is part of the assumption here. So I'm going to unify with that, and now my goal gets changed, right? I have a similar figure here, but what I need to show in terms of generation has changed, right? So earlier I needed to show that VC1 generates NS. Now I need to show that X generates NS, right? So I'm sort of coming down this arrow, and I need to take one more hop, and this is easy, right? This is just the constructor. So I know that taking a silent step will generate the same trace on X and X0. So I'm going to apply gen silent. This will ask me to show I can take a silent step, right? Which of course matches with the hypothesis here. So that's done. And finally, what I have is I need to show X0 generates NS, right? X0 generates NS. I know that VC prime generates NS. And in addition, I also know that there is this relationship, right? There is this R X1 that relates X0 and VC prime. And because I'm doing induction, I have the induction hypothesis, right? Which says that if you wanted to show that some VC1 generates NS, then you can just show that relationship holds. That is precisely what I'm going to do. I'm going to apply the induction hypothesis on this generation, right? Which will ask me to show that X0 and VC prime are related, right? X0 and VC prime are indeed related through X1, and that gets unified, and this goes through. Right, so that's the use of these many lemmas that we had used. So again, the last sub goal that we have is for the output step, right? So The difference is that here I have an actual output. I'm going to adopt a similar strategy. So I'm going to do match step, right? First order, clear all the tactics, and then write out what I have. So because of match step, what match step says is there might be multiple steps here, and then one step, right, where the labels match. This label is the same as the label here, right? And then these two are related. So that is what I've done, and the rest of the proof is going to be straightforward, right? So if you sort of apply the same backward step, I can get from here, right? I needed to show VC1 generates some ns. I can go from here to here. I can get it to be a goal on X, right? So let me do that, right? I apply the step. I needed to show E assumption. Let me do E assumption. So once I do that, I have the same obligation, right? So, but just lower down the arrow. So I needed to show that uh, given that VC prime generates NS, X, right, generates some NS. So this is also fine. Once you get here, we know we can take a single step where we generate this N. So I apply gen output, right? I'll be asked to show that I can take a single step from X to something. I can indeed take a single step from X to X0. So that goes through. And now you apply the induction hypothesis to match with the goals, right? So you do that, and the assumption makes it go through. So we've done the backward simulation as well. So let's just lift it up to this inclusion relation. And once you do that, we've done the forward and the backward. So now you can sort of show trace equivalence, right? So in this setting where you actually have multiple steps, we can show trace inclusion. So that's the theorem that we want to prove. So we've done that as well. So we've done the hard work of setting up this proof methodology for using to be able to prove and compile the optimization to be correct where it may skip steps. So let's apply it on the optimization that we had described earlier, which is that optimization which removes if statements if the predicate in the if condition is a constant. Then you can specialize it to either the left hand side or the right hand side, right? And the clever bit is that we needed to provide um, a particular value for this n, right? We needed to provide this constant n, and that needed to be just an upper bound. We just needed to say, okay, there is some n, so you can keep doing n numbers on the unoptimized program, after which you do need to match with the optimized program. And because we are removing ifs, we are going to count the number of ifs. And the way we are going to plug that n is we are going to count the number of ifs in the unoptimized program. And then we are going to say, pick this n to be 1 plus the number of ifs that we might possibly remove. It is not that we are going to remove all of these ifs. It just needs to be an upper bound, right? So we have this function which just counts the number of if statements, right? So the real thing is when you have an if, it says 1 plus the ifs in the subcommands, but everything else is 0. So this counts the number of ifs, right? Okay, so that is defined. And if you recall, one thing that we had done earlier is define something like this, right? We said, oh, there is this C-fold OK prime, where if you say, if I can step 0 from C1 to C2, then I can step from C-fold of C1 to C-fold of C2. So this was possible to be proven in the earlier example, in the earlier simulation, where we were matching steps 1 to 1, right? We were not actually eliminating any step. But this no longer holds, because if you sort of think about it, if I constant fold C1, it might be the case that I'm actually eliminating a particular if statement, right? And if I take a step, it might not be the same as constant folding C2 and stepping, because I might not have taken that step. So the steps will go out of sync, right? And here is an example, right? So if my program is say while 1, right? I'm using arith here just to say that this is a arithmetic expression. So then I'm going to do some other when inside. This doesn't matter. When next, then skip, else skip done. Else skip done. So if you constant fold this, then this whole thing gets eliminated, right? So this thing gets eliminated, and the whole program sort of gets to this one. So if I take a step in the unoptimized program, where I will get is that evaluation of this the body. But if I constant fold C1 and take a step, I actually get to one of these skips, right? Because when I constant fold, this is eliminated. And then when I take a step, I sort of go to one of these skips. So this no longer matches one-to-one, right? So I cannot prove this, right? And when you try to constant fold here, you will see that the outer F is eliminated. So you cannot prove this. So where will you so what do we do, right? We have to capture the fact that it is not that everything gets eliminated, right? So of course this sort of property, this property holds in many of the cases except this if, right? And what can we capture about that if? So here is a refined form, right? It says that if you can take a step in the unoptimized program, I go from C1 to C2 in the unoptimized loop. What are the possibilities? It is possible that I mean, if the step is not a if the step does not involve an actual elimination of an if, then you can go from the constant fold at C1 to constant fold at C2. That is possible. But in the other case, when you actually eliminate it, it must be the case that the label that you took here was in fact none, because that is the label that you because when you take a step in if, the label has to be none. If doesn't modify the valuation, so I sort of say v1 equals v2. Constant fold of c1 equals constant fold of c2, because you sort of took a step here, specializing to either the true or the false branch, right? Because you've taken the step, the rest of the program must be the same, right? So constant fold of C1 must be equal to the constant fold of C2, right? And this is for just the inductor hypothesis. So it says that the number of Fs in C2 is less than the number of Fs in C1 because we've eliminated one of the Fs, right? So you took a step here. You actually took a step in the if case is what this is all capturing. And since you had done that, the number of ifs in C2 should be less than. It's actually one less, but that doesn't matter here. So we sort of use less than because we're happy to do. We don't need the precise characterization. We just need this relationship, because we are going to reduce and eventually go to 0, and that is what our simulation relation with skipping actually expects. The proof of this is easy again, as earlier. I'm not going to go through the proof. Okay, so then there is some fiddling with applying this constant folding over context and then relating that to plugs, right? I'm going to skip all of this because they are not interesting. You can go through what it enables, but eventually we want to prove this, right? We want to show that this optimized version, which actually eliminates ifs but also constant folds expressions, produce the same traces as the original program here, right? So, and unlike earlier, where we just needed to instantiate this relation R, we also need to somehow instantiate this variable n, right? And the reason is that this n is sort of going to give us the upper bound of the number of silent steps that you can take. So what we do is we do simplify, and we are applying simulation skipping that we just defined in the module that we took effort proving. The key bit is this, right? So we are sort of instantiating this n to at least the number of ifs in C, and we are saying it is 1 plus the number of ifs in C. That is the number of silent steps that you can take. That's the maximum one, because those are, both of the steps are equally possible, right? You can either take a silent step where the silent step, the result of the silent step matches the right hand side, or you can take an actual step. So it just needs to be an upper bound. Excuse me. And then the actual relation is similar to the one that we saw earlier. So first matches, right? Second of VC2 is the constant folder version of the second of VC1, right? The right hand side of the right hand side program is the constant folder version of the left hand side program, right? So that's what we are claiming here, and that this helps us bound the induction, right? So it says that because we've set n to be 1 plus the number of ifs, it is always the case that as you keep executing, it is always the case that the number of ifs on the left hand side is always going to be less than the n that you picked. This is important because at every step we expect our relation to be n indexed, and this is sort of bounding the induction, right? It sort of says helps the induction relation. Yeah, and once you do that, the rest of the proof is sort of straightforward. I'm going to skip it in the interest of time. I encourage you to go through it in your own time, right? So what we've done with this is we've actually proved that the constant fold optimization is correct with respect to producing the same traces, right? So this is a general principle that lot of the verified compilers do, including ComCert. And in your assignment, which I will release a little bit late because there's still a lot of time, you will have to prove uh, code motion optimization correct. Not using, I mean, you don't have to use, it is not going to skip any steps. It will match one to one, just like the earlier version of the optimization we had seen. But the interesting twist is you will use um, um, something called a validator. So all of the details are described in the assignment. So so there will be a checker essentially on the site, and what you will do is you will not directly prove the optimization correct. You will prove that this checker, which sort of relates the source and the target program right, is correct. And if that checker is correct, then the trace is going to be the same, right? So it's just an additional twist, and the checker is how ComCert actually proves the optimization right. It's a very simple version of the checker. It's an interesting twist to the earlier one. So you won't be asked to prove any new version of the simulation relation. All the proofs will be given. What you need to do is to understand the optimization, right? It's a very simple optimization. It is going to move assignments over other commands. And when can you move assignments over? Only when the command that you are actually moving things over does not read the value of whatever was assigned, right? It's a completely independent assignment. You will be proving that right. This actually is quite interesting because producing correct code is very important, and you will understand a very important piece of how to write formally verified compilers. Oftentimes, what you'll see is that there is a lot of infrastructure that we've built. We've understood the principles, right? And we are applying it for small examples, right? So it may seem that all of this is a bit of an overkill for proving simple optimization. But what we are in fact learning is general principles out of this, right? And these principles are also applicable to larger programs. So as long as we know how these general principles work and we can apply them, we can even extend it to larger programs. But that's not the point of this course, right? This course is meant to teach you simple techniques. So you will learn a new technique while you do the assignment, and that will sort of we are using that technique to prove a simple optimization. But yes, but the point is proving that understanding that technique and that proving the subparts that need to be proved in that assignment. So yeah, so I think we have lots of time for the ongoing assignment right now. So I'll release that in a few days. Um, okay, so that concludes the compiler correctness part of it. What I'm going to do next is we are going to study. Where is it? So here we're going to study. Going to be yes. Okay. Give me 1 second. I thought I had it open. Okay. Okay. So we're going to study Hoare logic, right? So what is Hoare logic and why do you need to study it? Is the first question, right? Um, so let me make it full screen. This has to be 2021. Apologies for that. So what's the context, right? In the before we studied compiler correctness, we studied lambda calculus, right? So which sort of dealt with purely functional languages, right? So and then we studied this general property about some standard property about program correctness. So in lambda calculus, we didn't delve into what a specific program did, right? We sort of said, okay, here is lambda calculus, and we are going to study this idea of a type system, which gives us type safety, which means that if a particular lambda calculus program is correct, I mean, if a particular lambda calculus program is typable, then it does not get stuck. That's a property that we studied. Now, what we are going to do is to sort of go back to studying imperative programs, right? Um, in this setting, what we are going to do is not just study some overall property like soundness, type soundness. We are actually going to study deeper properties of the program. By deeper property, I'm just going back to what we had studied in a purely functional setting, right? That Fibonacci program actually computes Fibonacci even if you do it in a tail recursive fashion. Really, what we want to do is to say, okay, I have an imperative program that is probably computing the maximal element or something, right? I want to actually show that this, in fact, computes the maximal element in a set, right? And this may be implemented with the red-black tree. How do I, what is the logic that I actually use to study things that manipulate the heap? So we haven't studied anything about that so far. And in this lecture, we are going to study something like that. In particular, we are using an imperative language, which has a valuation, but also has a heap. And what is so special about the heap? Heap introduces all the complexities that you have by in C, right? If you malloc something and then you sort of do pointer manipulation, we are not going to do pointer arithmetic, but aliasing and pointers, sending pointers over, right? And then sort of reasoning about whether two pointers are equivalent. All of that will come into picture, and we want a logic where we can study programs written using pointers. I think the better analog to the C would be what you can do in Java other than C++, right? You can't just make a pointers. Pointers are going to be something, and you can't do arithmetic on pointers. That doesn't make sense. Just like Java, you have references, right? And you can transfer things by references. And I want the logic to be able to capture the complexity of what happens when you reason about heaps. And this is where Hoare logic comes in. And we are going to define the semantics of the program again using operational semantics. This is not going to be any different from what we've been doing so far. But directly proving complex properties about heap manipulations and so on using the operational semantics that we define will become tedious, right? So as a result, we will develop this logic called Hoare logic, which is a machinery for proving program correctness, in fact, automatically, right? So there is a lot of things that sort of fall out of this beautiful logic that allows you to automatically verify imperative programs, right? Automation up to some point after which you need to do something interesting, but it gives a way of automatically proving program correctness. I will hint about what that is later, right? So, but Hoare logic is a thing that allows you to reason about imperative programs, right? And it's just a machinery for reasoning about it. And it was invented by Tony Hoare, who is the same person who invented Pixar, right? So, yeah, I think he's sort of done a lot of fundamental contributions to computer science. This is perhaps one of the most important ones he did for program verification, right? He, along with a very few people, including Dijkstra, did fundamental work on program verification, and this is directly and this is sort of led to a lot of the beautiful tools that we have in production today, right? But it's sort of very, very small, and we will study core logic in our context. So again, because we are going to study an imperative language, we have to extend our simple language with support for heaps. We have the usual things for numbers, variables, right? Expressions. And then we have an additional expression here, right? When you see this expression, the idea is that it's like, I mean, it's a proxy for um, reading things out of the heap, right? Which is sort of similar in spirit to what you do in C, right? In C, we sort of say star P, right? Getting the value of P. This is very, very similar. So there is an expression which evaluates to some value, and the heap is indexed by the heap here in our world is indexed by a natural number. This natural number, you can think about them as addressees, right? Our memory, the heap in a C program includes addressees, right? And because we are in an abstract world, our addresses are natural numbers, and they map to natural numbers because that's the only sort of value we are going to deal with. But this introduces all sort of complexity, right? And this is just a reading value from the heap at whatever value this evaluates to. Because this is indexed by a natural number, if this evaluates to 1, this syntax is read the natural number at the position 1, right? And we have Boolean expressions in order to write interesting programs. So we have equality and then less than or equal to expressions. And for commands, we have skip, assignment, sequencing, if then else, right? And we have modifications in the other one. So this command, you can sort of read this very similar to star p equals some v, right? We are actually assigning to a memory location. So this evaluates to some memory location, right? It might mean, say, address 1 in the heap or 2 in the heap. And this command is the write to the heap, and it evaluates the right-hand side expression to some value and then updates the heap at that position. Right? So that is the meaning here. Our while is sort of the same as what we had seen, except that it has this prefix, right? And A is any assertion. It's an assertion with full richness of the assertion language. We assume propositional language, so you can use logical connectors and so on. So this is a language of assertions, right? And this assertion is actually, you can think about that as a function, right? That takes 2 arguments. It takes a heap and evaluation and says some logical proposition about the heap and valuation. It is intended to capture some property about the heap and valuation. Let's not get too deep into this. It is just going to be there for now. We will come back to why this is important a little bit later. And then we also have this assert command. This assert command is very similar to what you would do in, say, C or Java, right? Or even OCaml. OCaml also has asserts. So you can assert something where A is a assertion, where an assertion is just a function that takes the current heap and valuation, and A is a function that is applied on the current heap and valuation, and it's just arbitrary proposition. It can be false, true, or some interesting logical combination of properties on the heap and valuation. Right? That's the syntax. So the semantics of, let's look at the semantics of expressions first. So earlier what we had is we were interpreting expressions in a valuation. Here we will be interpreting exceptions in a pair of the heap and valuation, right? And the idea here is the usual things remain simple, right? If you the meaning of a constant is just the constant. The meaning of a variable is look up the value of the variable in the valuation. Addition, subtraction, and multiplication are just the interpretations of the sub expressions and the corresponding arithmetic operation, right? Equality and less than are very similar, right? And this is the new one, right? This is sort of the new one. And this is sort of reading the value in the heap at that position. So how do you interpret that? So the meaning of reading from the heap location is you interpret E, right? That could be a variable or a value or a complex expression as well. So you interpret E, that is going to give you some natural number, right? And the result of this interpretation is whatever the value of that natural number is in this heap. Our heap is just a map, right, from natural number to natural number. So it's just looking up the value of value at that position in the heap. So if this evaluates to say 10, we'll just return whatever value was bound at 10, right? And this is going to return an optional value, just like our valuation here, right? So the difference between valuations and heap is that this is indexed by variables. This is actually indexed by natural numbers. So I can just make up a natural number and index into it, right? So you can also make up variables, but variables are more restrictive. So that's the heap. And here's the big step semantics, right? So as I mean, we are sort of going back to what we had studied in operational semantics, right? We have both big step and small step. We will see Hoare logic applications for both big step and small step. For simplicity, we'll first take big step, and then we will sort of then go to small step semantics. So if you recall how we did big step semantics, our big step semantics sort of tell us what happens when the program completely evaluates to a particular value, right? And it terminates. So big step semantics cannot give meaning for non-terminating programs. And in our big step semantics in the operational semantics lecture, we had a valuation and a command, and that the big step evaluated to a valuation, the final valuation, right? Here, because we have a heap, our left-hand side of the big step evaluation includes the heap, right? Selecting the heap, the valuation, and the command, and the big step evaluates to a pair of the heap and value. So the meaning of the program, right? Whatever it does, it is its effect on the heap and the valuation, right? So that is the meaning of big step semantics. That is how it is organized. So each one, like, let's look at each one, right? So this is skip. Skip doesn't have any effect, so it just returns the same H and V. Assignment modifies the valuation only. So the heap is left as is. The valuation is extended with a new binding where this E is interpreted in H and V, and X is bound to that value, right? And similarly for assignment into the heap right, what we have to do is we have to interpret both E1 and E2, right? So so you have a H and V. The final result is it's going to modify the heap, right, and leave the valuation as is. So valuation remains the same. How does the heap modify? Now the heap is going to have a new binding, right? So our heap is just a map. So we add a new binding where we say interpret E1, right? And that is going to give you some location. It might be 0 or 10 or some arbitrary natural number. And what is the value that I'm going to store in this position? It is whatever E2 evaluates to. So if E2 evaluates to some value, that's the value that I'm going to bind here, right? That is the semantics of assigning into the heap, right? Sequencing is standard, right? So C1, C2, big step evaluates to V2, H2, V2. If you first evaluate C1, that gives H1, V1, and take this H1, V1, evaluate C2, and that if that gives H2, V2, then this whole thing gives H2, V2, right? Yeah, so this is if statement. So if B evaluates to true, I'm just writing it as is, right? So we are sort of using Booleans and propositions interchangeably here, right? When I write as B, interpret B in H and B and just leave it as is, I'm sort of saying this evaluates to some natural number. Actually, does it evaluate to a, oh yes, so sorry. So this evaluates to, so we have a separate notion of Booleans now, right? So we have a Boolean expressions here, right? So this can either hold or not hold, and we have a Boolean value here, right? So this is one of these things. It cannot be arbitrary natural number here. We have to use this Boolean expression here, right? I forgot to mention this here. This is different from what we had earlier. We did not have Boolean expressions at all. We were just using arbitrary expressions here, right? And we interpreted 0 to be false and everything else to be true. Here we are actually using Boolean expressions, right? So the meaning here is that if the Boolean expression actually holds, if it evaluates to say 5 less than 6, then that holds, right? If that holds, then we have to execute the true branch, right? You evaluate the true branch C1, and if that evaluates to H prime B prime, then the whole thing evaluates to H prime B prime. Instead of B evaluates to B does not hold, right? The way to read this is B does not hold. It is a Boolean expression. If that Boolean expression, if you interpret the Boolean expression and that does not hold, right? Then you have to evaluate the false body. So evaluate that. If it is H prime B prime, then that is the um, effect of evaluating this whole if expression, right? Which one do we do first? Okay, let's do while. So the first thing I want to mention about while is that this I that we have, which is this A that we have here, right? This is not going to have any effect for the operational semantics, right? We will use it for proving properties about the program. We won't actually use it for to give meaning for the program itself. So it's not going to be interesting for the semantics. It is only going to be used for the proof. So even though this I appears here, observe that we are not using this I in any interesting fashion. It is a proposition, right? It is some invariant. I'm not actually referring to this invariant anywhere, right? So that's the thing that you have to. I mean, there has to be an I here. It is missed here, but this I is just here. I'm not using it in an interesting fashion. So what is the meaning of a while loop? If the body of the while loop evaluates to a true expression, right? Then you sort of take the body once, right? And then build a new command, which is C semicolon, again the body again, right? And if that the whole thing evaluates down to H prime B prime, then this whole thing evaluates to H prime B prime. Of course, this does not give a meaning for non-terminating programs, right? That's the catch here. We will fix that when we look at small step semantics. Let's just keep it on the side for now. So if the body now, if the Boolean expression here does not hold, right? It does not hold, then we are not going to evaluate the body. So HB sort of remains as is. And we have this final thing, assertion, right? And this is interesting because how do you actually give meaning for assertion? In C, right? If you have an assertion, if the assertion fails, the program just terminates, right? Similarly, in OCaml and Java and so on, it just throws an exception or terminates or does something, right? So how do we capture the meaning of assertion in our operational semantics? The way we sort of do that is the only thing that we have in our hand is we can make the evaluation get stuck, right? If the evaluation gets stuck, if the rule is not applicable, then we can signify an error condition. So recall that we use this notion of getting stuck to give meaning for what lambda calculus, simply type lambda calculus actually gives you, right? We said if a particular term type checks, then it does not get stuck, right? If the assertion fails, we want the rule to not apply so that the program gets stuck, right? So that's the idea here. It's an interesting way to encode, capture these semantics, right? So it says HV assert A. I'm going to, so recall that assertion is actually a function on nature V, and it is arbitrary property, right? So this is interesting because I'm saying that if A HV holds, right, then you just evaluate to HV. So the whole thing evaluates to some pair of H and V. If this assertion does not hold, then this rule does not apply, right? You cannot show that the premise actually holds. So you cannot apply this rule, and this evaluation will get stuck. So that is how we sort of capture what happens um, when assertions hold, and when assertion does not hold, this rule is just not applicable. So you'll just get stuck. The evaluation will get stuck at this position, right? So that is how we capture the meaning of assertion. Any questions on this? How we've defined the rules? No questions? Okay. So you will often see this trick, right? So when you don't want something, when you throw an exception or when something bad will happen, you will just, in the operation semantics, not have a transition for that. And our way of capturing assertion here is the transition actually is only present when the assertion holds. When it doesn't hold, the rule is not applicable. Right? So that's the cool trick that we kept reusing over and over again. Right? So we've not. This is not the first time we are seeing this trick. So I'll just mention this and conclude the class. So in Hoare logic, we have what are known as Hoare triples. Right? You will see this condition over and over again. It is written using this syntax. So curly braces, you have a P, and then you have a command, and then you have a Q. And this P and Q are what are known as pre and post conditions. We've seen pre and post conditions a little bit when we studied F star. I mean, that is, it comes from here, right? So the whole point is you want to express some property about the program here. It can be an arbitrary property. You can say the initial heap does not, everything is 0, right? And you execute this program, right? And you are sort of claiming something else holds at the end of the program, which is Q, right? So PQ is just a function, right, that goes from heap to valuation to prop. So this is some property that you want to have before you execute the command, and some property that you want to have after the execution of this command, right? The property itself can be as complicated as you can imagine, right? This can say initially the heap contains a list of numbers, right? Um, and then the final condition can say this list is now sorted, right? And you capture the notion of what is sorted in this post condition, right? And the command could be a sorting a program for sorting that list, right? So this is a general way of writing it down. This might, again, the way to read this is this might or might not hold, right? When you write a Hoare triple that sort of captures something that you've written down, we have to sort of prove, we might have to prove that this Hoare triple in fact holds, right? And the nice bit of this Hoare triple is it sort of breaks down nicely. So instead of proving this on the entire program, we will sort of look at Hoare triples for each of the commands. Because our program itself is built out of individual atomic commands, we will see how the Hoare triple sort of is applicable to each of the individual commands. So if I have sequencing, then I will say, oh, you have a pre and post condition, then there has to be some intermediate condition, which is now given by this first command. And you take that intermediate condition, that becomes the precondition for the second command, and you then have to show that the post condition actually holds under that, right? So the intention of having this pre and post condition is that they capture the abstraction of the program behavior, right? So this program could use merge sort or quick sort or whatever sorting you capture, right? But this pre and post condition need not care about the details. It might just say what it means to be sorted. Again, this can be very complicated. It can do in place merge sorting, for example, in place quick sorting, for example, right? And what we want to capture from the high level is that I don't care about whether it is doing in place quick sorting, right? I might just want to care about that the input list happens to be sorted in the result here. I mean, that is my core high-level property. Core logic actually tells you how to sort of break this apart and prove individual pieces of the program, right? And this leads to a nice automated program verification procedure. We will sort of badly simulate this automated program verification procedure using our Coq automation rules. But in real world, you sort of use Hoare logic as a way to prove complex C programs, right? And we discharge the proofs through SMT solver. You've seen SMT solver in FStar, but these combinations are often used in an interesting fashion. You will see what this allows you to do in the next few classes, right? So keep that in the back of the mind, and then we can sort of delve into details about. You'll see small programs and how we prove things and so on. So I'll stop here, and then we'll catch up from um, next week, right? So today's Thursday. So we'll catch up next week. Thanks, everyone. Talk to you later. Bye.